Okay, we'll continue. So, right. So we know what the derivative represents. What does the derivative represent on the graph? So if I have a graph here, and I have my y equals fx, what exactly is the derivative? What does it represent on the graph?
The area.
No, you're going too fast. Derivative.
Oh, derivative.
Yes.
Gradient.
Is the slope, the gradient, yeah. So the derivative represents the gradient, the slope. Yeah? So now what we'll have a look at is what exactly does the definite integral, the antiderivative, represent. So for example, this here, if I said this, I would mean the slope of the tangent at x equal to a. What we did last week. So then the question is, what does this represent? Let's have a look. Okay, so you'll need this. So let's say that's x and that's y, and here we'll make x, and then here we'll have x plus delta x, and then here is our function. So here would be f of x, and then this one here would be f of x plus delta x. Okay, so write that down so far. Oh, keep it clean. PG-13, please. Okay, can I go on with this? So, for a moment, we'll see why now. If I draw straight lines here and make a shape, I know it's not perfect, but this shape that I make is roughly equal to the area under this curve, roughly. So I'll just call that AX. So I can say AX is roughly this area. So I make this into two shapes. So we have the base, and then we have a triangle on the top. So how big is the base? It's delta f. And what's the height of the rectangle? Fx plus half the base, and then what's the height of the triangle? Yeah, it's the fx plus delta x minus fx. Okay, so let's clean that up a bit. So that's delta x fx plus a half delta x fx plus delta x minus a half delta x fx. And then you see, this here is the same as this, so I can put them together and make a half delta x fx plus a half delta x fx plus delta x, like that. Continue? Yes? Okay. So anyways, you might say, you can clean this up a little bit because there's a half in both and there's a delta x in both, so you could change this into delta x over 2 fx plus fx plus delta x, like this. And this is our ax. Okay so far? Yeah. Now, if you remember, you had the formula, the derivative. Well, let me see what I do. Yes. Now what I want to do is I want to calculate. What do I want to do next? Let me think. Yes, actually, I called this AX, but I actually need to be a little bit clearer here. So I'm going to call it a different thing, not AX. If I just go to the side for one moment. Okay, so here's my curve. So this here is AX, okay, and then this piece here in blue, so there is X, and here in blue is X plus delta X. So the blue area is area X plus delta X. So the piece I'm looking at in here is the piece in between the two. So if I go back to my picture here, I called it A, but maybe, well not maybe, I just need to put in here, I should have put in a delta here. So if you can just add in delta here. Yep. Okay. Now what I'll do next is I'll divide by this delta x. So delta A over delta x equals fx plus fx plus delta x all over 2. And what happens when the delta x goes to 0? So if I make the delta x 0, what does this become? If the delta x becomes 0, what does this become? What do we call this? Remember when we had delta y over delta x? And this becomes 0? Yeah, what is it? No. Oh, no, don't do that thing where you pretend you don't know what it is. So do you remember last week, delta y, delta x, and then delta x becomes 0. This becomes... Oh no. Yeah? Did you? Okay, I didn't hear you. Thank goodness for that. So on the left, this becomes dA dx, the derivative. And what do I get on the right here? Well, I get fx plus fx over 2, which is what? Fx. So the derivative of the area is equal to fx. So then that means the area must equal the antiderivative of fx. So anyways, that's the result I wanted to get. that the meaning here of the antiderivative is that it represents the area on the graph. So, just to put those results up the side here, fx, what does that represent on the graph? The height, of course. And what does the derivative represent? That's right, the slope, yes. And then now we have the new result that the antiderivative represents the area. So these are our three situations we have. If I want the height, I look at fx. If I want the slope, I look at the derivative. And if I want the area, I look at the antiderivative. Let's have a look at an example. Can I go down? Yes? So this is the reason why this topic is so important, because it can let you find areas. So as you know from economics, one application of finding the area on the graph is to find the consumer surplus or the producer surplus. You've done this, haven't you?
Yeah.
Yeah. So on your, can I go down? On your graph, this is Q, isn't it? And this is P. And then the demand curve goes, the consumer graph goes down, isn't it? Yeah. And then the supply graph goes up, like this. And this is the, what's this point called? Equilibrium, good. So this area on the graph is the consumer surplus, and then this area here is the producer surplus. So when you do this, the shapes are simple, they're triangles. But in real life, your graphs don't ever look like this. The graph will go, there'll be one graph will go like this, maybe, and then the other graph will go like this, or something weird like that. So then the consumer surplus, you have to get this area, and what the heck is that? It's some kind of triangle thing? Something. So this is one of the reasons this topic is important, because it lets you find area on graphs, and as you've seen from economics, the area on the graph does mean something. I think is this the only example of area in economics you've used for graphs? Is it? You haven't done anything else where you have to calculate the area in economics? No? No. By the way, have you done marginal revenue and marginal cost? Yeah, let me show you something here. So for example, if you had something like,
Not yet.
oh, you haven't done it?
We didn't.
All right. Some of you have done it. Right. All right. Well, you have heard of marginal revenue and marginal cost before. So, for example, cost or total cost will be the fixed cost plus the variable cost. So, for example, here's an example of cost: 20 plus 5Q. Yes? And what's the derivative here? It's 5, which is also the marginal cost. So, in fact, here's an example of derivative in economics. One definition of marginal cost is the derivative of the total cost. And marginal revenue is the derivative of the total revenue. And then marginal profit, you get the idea here, what would that be? It'd be the derivative of the profit. Yeah? So I mean, you might think calculus not for me, but again, if you're doing economics, you'll do this stuff in first year again. Okay. Let's have a look at an example now. So let's take this function here. Okay, so let's write this one down. Y equals x, something simple. So 0 to 2. And what would be the height here? If this is 2, what would this be? 2. So if you want to calculate this area here, you know what the answer should be because it's a triangle. So we're doing something simple first. And what should the answer here be? Well, how big is the base? 2. And the height? 2. So a half 2 by 2 is 2. So the answer should be 2. Let's see what we get if we use this new method. So the area should equal 0 to 2, because that's these numbers here. X, because that's our graph, is x dx. So this would be x squared over 2, 0 to 2. This would be 4 over 2 minus 0 over 2, and it works out exactly right. It's 2. So it gives us the correct area. Now let's use this for a shape where we don't know what it should be. Continue? Right. So let's take something like this one, 0 to 1 again. Y equals x squared. Right, what should this number here be if I need it? I don't need it, but it should be 1, but I don't actually need it. Right, so if I want the area here between 0 and 1, the area would equal 0 to 1 x squared dx, which equals x cubed over 3, 0 to 1, which would be 1 over 3 minus 0 over 3. So the area is 1 over 3. So you know this area is 1 over 3. So now we have a very powerful way to find areas of lots and lots of different shapes and curves and graphs. So when is there a problem? When do we need to be careful? Can I continue? So we need to be very careful if our graph goes above or below the axis. So for example, let's say this is 1, and then this is 2, and then this is 3. And I want this area. Or even something simpler. Here is 1, here is 2, and I want this area. It's not quite 1 to 2, f of x dx. Yeah, when the graph is under the axis, like it is here, the sign will be wrong. You need to put a minus in front to correct it. Not a big deal. But the problem is much worse if it's mixed. We definitely cannot say this is 1 to 3, f of x dx. You can never ever mix them like this. The only way to do this one now is you need to separate into 2 problems. The positive area and the negative area. So what is the positive area? Well, that would be 1 to 2 f of x dx. And how big will the negative area be here? Well, that would be 2 to 3 f of x dx, but I need a minus in front. Now this gives us the correct area. Yeah? So in other words, my point is, if the graph is under, we just simply put in a minus. No big deal. If the graph is mixed of above and below, we need to separate it into 2 problems. The positive part of the graph and the negative part of the graph. So we have 2 antiderivative problems.
Do I have
Not a big deal, but longer. Yeah?
Like get the root of
And this is another thing too, which we'll get to now. Okay, can we have a look at some more examples then? Okay. Right, so what I'm going to do is graph this function here. Too much. Right. So what I want you to do is write down this function x squared minus 3x plus 2. X squared minus 3x plus 2. Can you see it? Yeah. So for this problem, what I want to find is this area here between the graph and the x-axis. So this area right there. So it's an integration. From the graph, I need to integrate from where? Where do I start and where do I finish? From 1 to 2. But of course, in the exam, you don't have this graph. So how could you find the 1 and the 2? Factorize, yeah. The 1 and the 2 are roots of the quadratic. If you use the quadratic formula on the quadratic, you get 1 and 2. So they're the roots there, 1 and 2. So what would the area be? It'd be integrate from 1 to 2, the quadratic. And there's a problem. It's under, so we need to put a minus in front. So what I want you to try first is I want you to get the area for me, then I'll do it, okay? So I want everybody to get the area here for the quadratic. Can you try? So it's x squared minus 3x plus 2. Okay? Let's have a look here. So the area will be minus, and this is 1, and this is 2. These are the roots of the quadratic. Minus 1 to 2, x squared minus 3x plus 2. This is minus 1 to 2, x cubed over 3 minus 3x squared over 2 plus 2x, which equals minus. Now, let's put in the 2 and then let's put in the 1. Right, so 2, that would be 8 over 3 minus 2 squared is 4 over 2 is 2, so that's 6 plus 4, and then this would be 1 over 3 minus 3 over 2 plus 2. Okay, let's clean this up. 8 over 3 minus 1 over 3 is 7 over 3. Minus 6 plus 4 is minus 2. Minus 2 minus 2 is minus 4. So this would be 4 minus 7 over 3. 12 over 3 minus 7 over 3. 5 over 3? Did you get 5 over 3? Well, let's see what the computer gets. Maybe I made a mistake. I'm not going to discount that.
Maybe you are right.
No, no, no.
Yeah.
Yeah,
1 over 6,
yeah,
not 5 over 3. So where was my mistake then?
yeah.
Right there, is it?
There.
Let me see. 8 over 3, 2 squared is 4. Oh, not 6. Oh, no, 4, 2, 6. Yeah, 4, yes. Minus 1 over 3, minus 3 over 2, plus 2. 8 over 3. Oh, not 7 over 3. 5 over 3. Here. 8 over 3 minus 3 over... Oh! 4 over 3. Hang on. I better go back. Mistake happened here. Let's try this again. 8 over 3 minus 1 over 3 minus 6 plus 4 plus 3 over 2 minus 2. Okay, let's try this again. 7 over 3 minus 2 minus a half. I'm going to use the calculator. Yes, exactly the answer, 1 over 6. Okay, let's look at something a little bit more difficult. So here's a cubic. You know the shape a cubic makes? So we have the area, we want the area between the curve and the x-axis. So what's the problem here? What do you not know? The roots. How do you find the roots?
Yes.
How do you factorize? First you need to guess. So, I won't do that because we did a lesson on that. First we guess. So is 0 a root here? No. So if we try 1, we get 1 minus 6 plus 11 minus 6. Is that a root? If I try 1?
Yeah,
1 is a root, so then what's the factor? If 1 is the root, what's the factor? X minus 1. So then what do you do after you find the factor? You do the long division. And then after the long division, you get a quadratic, and then after the quadratic, you factorize it. So easy. So quick and easy to do. So we have 3 roots here. What are the 3 roots? 1, 2, 3. 1, 2, 3. So I kept it easy for you. 1, 2, 3. So if I graph this here, 1, 2, 3. Okay. So we want to find the area. So we need first integrate from 1 to 2. Actually, hang on. Let's try. Yeah. Integrate from 1 to 2. And also integrate from 2 to 3. And how do we put the answers together here? There's a minus. So, up the top is the cubic. First we get the positive area, then we get the negative area. But what's the problem with the negative? It's negative. So we stick a minus in the front to fix that. So in your head you can think of this as 2 separate problems. You can do 1 to 2 first, then you can do 2 to 3 second, and put the answers together. Okay? Now at this point, I don't want to go through that again because you've done, the last lesson was about calculating these things. So for example, maybe we'll just do it out loud. What does the cubic become? It'll be x4 over 4 minus 6x cubed over 3 plus 11x squared over 2 minus 6x. Which number do you put in first? 2. And the next 1. And then how do you put these together? With a minus. Repeat the process for line number 3, but stick a minus in front of your answer. Now you have 2 answers to finish. Just add them together. Okay. By the way, there's still one more example to show you. Sorry, took break, I know. And so again, I just want to outline the process. But there's still one last type which we haven't done. So these are problems like this, where you have one curve which is high, and then maybe another curve here which is lower, or something like this. And I don't want the area between the curve and the axis. This time I want the area between 2 curves, like this. So this is now more like what you have in economics, where you have one curve, another curve, and maybe you want the area between the curves. So the big curve here I'll call F, and the one that goes underneath I'll call it G, and we'll say it goes from A to B. And I want this area here. Does anybody know how to get this?
Minus 8.
That's it, very good, yeah. Very similar, all you need to do is integrate from A to B, but not F, not G. You need to find what F minus G is. So let's do a quick example. Here is F, y equals x. Here is G, y equals x squared. And I want this area. So what do I need to do first? What do I need to find first?
The roots.
Not really called roots, because it doesn't cross the axis. That's not what I want.
Like vertex.
Not this word. Wow, I just want to find
Which
first.
one is the maximum? Which one is the
Not this either. I want to find where they meet. Intersection. Intersection. So you have 2 equations, y equals x and y equals x squared. Have you seen this lesson before? You have. This is called one linear and one quadratic. So you've learned how to solve these. What's the best method to use here? Elimination, substitution, what? Here, substitution. So you get x equals x squared minus x equals 0, x equals 0 or
minus
1. So here is 0 and here is 1. So the area will be integrate from 0 to 1. Which is first, x squared or x? Which is higher? X or x squared? X minus x squared. The top one minus the bottom one. Dx.
But sometimes we don't have a graph, so you big number you need to know which one is.
No, if you don't have a graph, you might have to do a quick graph to get an idea.
No, to get like which one is minus another one.
Which one is minus?
Like you know it's from the graph. X is
Oh, which is higher?
yeah.
Yes, maybe, yes, yeah. Okay, what's the integration of x? X squared over 2, and then this one? X cubed over 3. So this will be 1 over 6 when you put in the numbers. So just one last thing actually maybe to say here. Do you have this? Yeah. So for example, this is P, no, this is Q, this is P, like X and Y. This one here is called the demand, isn't it? So I'll just call it some function, or what letter do you call it? That's what I was going for. Yeah, really, seriously? And this one, it's a function of Q, and then this graph here, I don't know, whatever, supply, and it's also a function of Q. Q is like the X, so here you have like P equals P equals. It's like Y equals F of X. So if I want this area here, this one here, what would that be? Well, you would have to find the equilibrium point. Let me just call it, what letter do you call it? Don't say E, is it E? The same letter here? Do you not even maybe put a Q0? No, it's the same letter as this? QE maybe? Alright. QE then. And here is 0. Yeah. Now, here you can imagine there's like a rectangle here. How big is the base? QE, and the height here would be, this would be PE, the price at equilibrium. Right, so 0 to QE, supply or demand? Demand, integrated. What does this give me? Does this give me what I want? No, this gives me all the area here under the curve. I don't want this piece here, do I? So I have to do a minus what? QE PE. So you could define consumer surplus as an antiderivative problem. Now this is important for the business and economics students because when you go on to university, this is exactly what you do in your microeconomics year 1, semester 1 class. I know this because I give private lessons to people who have failed their first year exams in economics and they have to repeat this. So I know for a fact this is what you do. In the real life, the lines are not straight, they're curves. Okay. Now let me tell you which ones to do before you go. So okay, can you do 1, 2, 13 and 21? Yeah, so it's 1, 2, 13. 21 is the second last. You write this down? Huh? This you could use to calculate consumer surplus. That's right, yeah. You can put. No. The P must be after the integration. So this. Yeah. Oh, I see what you mean. Then, let me see, where's your formula? Oh, PE, no Q. Yes, okay. You took the Q out, so you're right, this also works. Yes. So this, what do you want to study next year? So if you do an economics class, you might get something like this. Yeah. Okay. Yes. Okay, do you have it now? That's fine. Sylvia has it? That's fine. No